Hi everyone, welcome to this video where we will continue to learn how to use aXis2000 for stick-sum data analysis. In the previous video, we looked at how to clean the data, for instance, to remove bad lines, to remove bad images, and perform alignment of images within the stack, to extract spectra from the image stack, and also to convert data from transmission mode to optical densities. Today, we will walk through key methods used to analyze the data. Stick-sum. Stick-sum method gives us an incredible insight into complex information contained in your samples by combining high resolution imaging and spectroscopy information. But the challenge is to make use of this complex information generated. That's why it's important to perform advanced data analysis, for instance, by applying fitting techniques to understand the chemical composition of your sample. To perform this task, we use this function stacks. Go to the map, and we will focus on SVD, which is a singular value decomposition used to convert the image stack into component maps, and also stack fitting, which is based on linear regression. Let's begin with SVD. If you press SVD, the software will ask you to read the input file. The input file, let's work on this sample. The input file is your image stack prepared on optical density scale. So if you want to see how to do this, please watch the previous video where we saw how to convert data from transmission to optical densities. But also the data should be well cleaned, and also the images within the stack should be aligned. All that information can be found in our previous videos. So here I will press this, which is my input data, and read fit parameter file or no. The software will ask me a number of components. The number of components are the components or the chemical species that you want or that are contained in your sample. This depends on how many and what type of reference compounds you provide during your data analysis. So it's important that during the data collection, you have some preliminary knowledge about your sample, and while you collect the data, you also collect the data for your reference compounds. You can use these reference compounds to do the fitting. That's what we are going to do. But also, there is a way, if you know your sample well, you can also obtain internal standard by extracting the spectra from your samples. So in my case, I'm going to use 3 standards. You can use whatever number you want, but it's important that you make it as correct as possible, because you know better your samples, you know what reference compound spectra you can provide. So I enter number 3, press enter. So the software will ask you to load those reference spectra. Excuse me. They are contained here. So my first standard is going to be calcite. So the reference spectra or the spectra should be saved as a text file for aXis to be able to read them. So I first read calcite. It's important here to give it a short name. I can remove this unnecessary information. The reason why here is the output, which is the component map corresponding to calcite reference compound that I'm reading. It will have a name which is a combination of the reference compound you provide and also the root name. The root name is the input file that I read right at the beginning, which is my image stack. So then I have deleted unnecessary information. This is to avoid to have a very long component map name. So I press enter because I told the software to use 3 reference compounds. It asked me where is the second. I want, for instance, let's say aragonite. It's just an example. I remove this information. So the third, let me use, for instance, calcium chloride. So after reading all 3 spectra as text file, I can save them, for instance, SVD. The software asks me to save. Clip at limits, no. So this is the root name I was talking about, which is the name given to my input file, as you have seen before. I press enter. Save residuals. Yes, I can save residuals. Let me call it residuals. So this is the output. So the output, the first output saved in buffer number 4, it's calcite. The second is aragonite. The third is calcium chloride, according to the order that I used to read my reference compounds. As I told you, the output name of the component map consists of the name of the reference compound used and the name of the root or the root or the input. This is why I was telling you or advising you to just use a short name so that you avoid to have a very long name. So here I have 3 species, 3 component maps. One corresponds to calcite, there is aragonite, there is calcium chloride, but also there is a residue. So these maps, this output means that this is what is contained in the sample according to the reference compound that I have provided. So I can save them, but before saving them, I can also do some processing. I can, for instance, let's click on calcite and go to image, clip signal, histogram. You see from the histogram, the optical densities consist of positive and negative. In fact, they can't be negative. This is why I'm going to cut out the negative values and remain with the positive values. So here I can I left click in the 0 and then click somewhere towards the upper limit. I can choose to only stop where the histogram ends or to go up to the maximum. When I'm done, I should copy the map and place it in the buffer. You can place it in another buffer if you want. So I do the same for aragonite. I first click on this aragonite, use the function images, clip signal, histogram, remove the negative values by left click on 0 and do it again on the upper limit. When done, copy the buffer here. I did the same for calcium chloride, images, clip signal, histogram, choose 0 and the upper limit. I can also do the same for the residuals. So this was okay. So when you have this 3-component map, you can have more. I can save them if I want. To save, as we have seen previously, we use this function write. But first, you need to click to the component map that you want to save. Let's say calcite. Go to write. You can save at an XCB file or as GPG, PNG, TIFF. Let's choose TIFF. TIFF image. Call it calcite. If I want to save the aragonite, I have first of all to click on it, right? Function, graphics, TIFF images, aragonite. It will be saved as a TIFF. The other one is calcium chloride, right? Function, graphics, TIFF images, calcium chloride. Yes. So when I'm done, I can create RGB composite map to see how these components are spatially distributed across the sample. So to do that, I go to display, RGB composite. So this is a widget showing 9 buffers, which correspond to these ones. Remember, calcite is in the 4th buffer, aragonite 5th buffer, calcium chloride 6th buffer. You assign a color according to the buffer. Let's say if I want calcite to be red, I will press 4, and in this case, it will be assigned the color red to the color red. So I press 4. What compound I want to be green? Let's say I want calcium chloride to be green, then I will press 6 because calcium chloride is in green, 6. And then aragonite will be blue, then I press 5. You can choose to auto scale each component or no. Let's do both and we will see the difference. Let's first accept yes. I can save it, maybe RGB1. So this is the RGB composite map looks like. You can see that according to the information I provided to the sample, such as the reference compounds, the most or the dominant phase is aragonite. I can also save it without auto scale. I go to display, RGB. So let's calcite be red, calcium chloride green, aragonite blue, then no. RGB2. So you can see the difference. You can play with different way of saving the RGB composite, and then you can decide what you want to do. So this means that according to the information provided while performing singular value decomposition, it looks like aragonite is the dominant compound in this sample. So it all depends on the reference compounds that I use and also your sample. So you know better your sample. It's very important to have the right reference compounds. So this is about the SVD, and in the next video we look at how to perform fitting of image stack by using another tool, stack fit. Thank you very much for following.